So thank you for having me. My name is Giuseppe Pasquale, and today I will present my progress on my PhD thesis that I'm carrying out at TNA Space. So my supervisor is Professor Manuel Sanjurjo from UC3M, and from TNA Space, Dr. Daniel Perez Grande. Borja covered it already, so very briefly. What we do at TNA Space is, as Borja covered very well, Athena, so this propulsion technology, which is a modular propulsion technology, it's highly customizable. You can select fundamentally the thruster heads, so the emitters, and which impacts the thrust and the power level. But you can also set fundamentally the tank, the size of the system. So this is coupled to the design of the mission. So what we do as well is tools for mission analysis, which are Go and 360. And my thesis mostly focuses on 360, which I'm going to talk about. Just to give you a bit more on the problem motivation very quickly, the problem, as I said, is highly coupled. So you can't really design the mission, your propulsion system without designing the mission itself. And it's something that you need to do from the beginning from the early phases. And it's something that you bring up to the operational phases. It's something that goes through the whole life cycle. So the goals of my PhD were starting from the first one, the development of this commercial software for optimal guidance of low thrust in LEO. The focus is in LEO, which then branched into thrust design and optimization, concurrent subsystem design, and more into constellation deployment and logistics, which is a big topic now also with electric propulsion, if we think about, for example, Starlink or OneWeb. So all of this went into this tool, 360, as I mentioned before, which we are releasing right now. So finally, after a couple of years of work, we're starting to really bringing this to the industry. And my second, let's say, objective was the development of these attitude control laws coupled to the optimal guidance obtained from 360, which is something that kind of now is a bit secondary in the thesis, and I'm going to mention a bit of this work in the end. All right, so I'm going to focus now on the methodology and the results. So as I mentioned before, the problem is actually highly multidisciplinary. You have a lot of couplings between different disciplines. You can see here this metrics that actually shows how trajectory and propulsion are coupled through different variables. But in reality, especially with electric propulsion, you have couplings also with the power system and the ADCS. So you actually have a problem that's quite complex because it covers several disciplines. And additionally, if you do this, as I said before, early in the design life cycle, you might want to cover this as a multidisciplinary problem. So you might have multiple objectives, multiple constraints, multiple variables as well, of course. So to give you just a first example, this is a case in which we're optimizing the maneuvers, so the trajectory, but also the propulsion system in this case, Athena. So regarding the trajectory optimization, the way it's done, you can see here some equations. This is a predefined control law, which fundamentally, it's a different way of optimizing compared to more classical methods like direct or indirect methods. Because you have this sort of predefined control law, and then what you can do is actually optimizing the gains of this law, which leads to near optimal solutions. They're not as good, let's say, in terms of optimality compared to other methods, but they're very robust. You will always converge fundamentally to a solution. So the thing that we do here is using this genetic algorithm to solve for the weights of the trajectory for this predefined control law, but also for the design of the system. So in this case, we're treating, as I said before, a multi-objective problem. So the usual solutions that you get is these Pareto fronts. So you have the two objectives and you can plot them and you get these points that each point represents a solution that is a given, it's a given trajectory, but also a given propulsion system. So in this case, as I said before, we have Athena that is this modular system, and you can recognize some families of solutions depending in this case on the number of emitters and then size of the tank. So we can extend this problem, as I mentioned before, also to including other subsystems. So in this case, the EPS. And what you see is actually that if you have this more holistic approach, you can get improved Pareto fronts. So as you can see here, the solutions now are better because we are actually considering the broader problem, the more multidisciplinary problem. And this leads to these improved solutions, also a more complex actually spread of the Pareto front. But again, we can recognize some families, in this case, related to the configuration of the solar panels in this particular problem. Another topic that I covered, again related to the first objective, is that of constellation deployment. This is another quite big problem, let's say, topic right now, because we have, for example, OneWeb, Starlink, that they're all using electric propulsion to deploy the constellations, because you can get significant saving in terms of cost. You can reduce fundamentally the number of launchers that you need. And the way this is done is by exploiting the J2 perturbation. And in my work, I also use combination of orbital elements, which is something that is a bit, well, I would say new. And in these two papers, I studied two methods, a parallel and a sequential method, which I think discussed last year, so I'm not going to focus a lot on this. But in principle, the parallel method can be more efficient when you don't have injection constraints. But the other method can become more interesting compared to the other one when you actually have injection constraints. A novelty, let's say, from last year is actually this variable performance optimization. This is, again, something very peculiar to electric propulsion, is the thing that you can actually modulate, not with all the propulsion system, but with some of them you can actually modulate the performance instantaneously throughout the maneuver. And if you do this, you can actually improve the optimality of the maneuver itself. Now here, this is a bit in a nutshell like the methodology that I implemented. This fundamentally ties this maneuvering efficiency, this parameter, to the performance of the thruster, to the specific impulse in this case. And you can find this kind of solution. So the blue one, the dashed blue one, is for the constant case. And if we implement this methodology with variable performance, you can actually see this improved Pareto front. In a point, we actually have 18% of saving in around 18% for both the objectives. If we look at some of these solutions, you can clearly see how the ISP varies throughout the maneuver. So in principle here, you're exploiting better the dynamics, and you're getting simply just a more optimal solution. This also has an impact, is impacted significantly actually by the technology. So you can see, for example, that some technologies actually retain a lot of gain compared to a constant efficiency case. While, for example, in this case, this is a grid and ion engine model for the efficiency, is not very convenient to do this variable performance. Finally, I'm going to mention two works that I have actually, from two students that have been the relator for their master thesis fundamentally. The first one is from Brandon Escamilla from UC3M. This is an extension of my work on constellation deployment because we wanted to see what happens if we consider also the launcher selection. So the logistic of the launcher, that's something that actually impacts significantly the problem coupling. So then the first aspect from my papers with mixed integer programming for the selection of the launchers. And we did some work here with Pareto fronts from cost. In this case, of course, you need to use an objective that is more, that takes, you can't really use mass, but you need to consider also the cost of the launch versus time. And the second work, this is from a student from Politecnico di Torino, Gianni Pecora, and this was more on the second topic, so the use of robust attitude control to fundamentally for attitude control using Athena, so this cluster of our propulsion system. And in this work, we applied the dynamic super twisting sliding mode control, and we obtained some interesting results. So I'm going to finish with some dissemination activities. These are the presentations I did previously, so I already talked about this. The new ones are the presentation at the International Astronautica Congress. This was September 2022. Then a presentation at the SciTech 2023. And this is the upcoming one in the UCAS. I will be presenting a paper, again, based on the variable performance, but also these two papers that are actually based on the two master theses that I described before. And in terms of publications, so this is an old one, this is a new one, so the conference proceeding from the IAC, a journal paper on the constellation deployment that I mentioned before, again, a conference paper from the AAA, and it's upcoming another journal paper and the conference proceeding from UCAS. And finally, just some extra activities. So participating in this ESA concurrent engineering workshop, which I highly recommend. It was a great experience organized by ESA. As I said before, supervised these 2 master theses. I'm supervising another bachelor thesis and some activities in mentoring SGAC. I presented twice at the Semana de la Ciencia, hopefully this year as well. And finally, participation in different seminars. And yeah, I wanted to leave it also with some pictures, just as because it's been 2 years and something, so it's a lot of memories. And I think it was nice to finish it with some pictures and a final group picture of the team at TNA. So thank you very much. If you have any questions, I'll be happy to take them.